In this session, we're going to look at permutations and ways of counting. Yeah, I know, you've been in school for how many years, and now you're going to learn how to count. The counting is based on something called the fundamental counting principle. And the fundamental counting principle is illustrated by our first example. A new car can be ordered in any one of 9 different colors with 3 different engines, 2 different transmissions, 3 different body styles, 2 different interior designs, and 4 different stereo systems. The question is, how many different cars are available? Okay, so let's look at these options. We've got 9 different colors available, 3 different engines, 2 different transmissions, 3 different body styles, 2 different interior designs, and 4 different stereo systems. So let's suppose that we have selected a color, we have selected an engine, we have selected a body style, an interior design, and a stereo system, but we're not sure about the transmission. We don't know if we want a manual or an automatic. Well, it's clear that there are 2 different styles possible with a specific color, engine, body style, interior design, and stereo. One of them would have transmission number 1, and one of them would have transmission number 2. In other words, if everything is already selected, then we have 2 different cars that could be made depending on the transmissions. Now, let's suppose that we're not sure about the engine either. With each of those transmissions, we could choose any one of 3 engines. And so now all of a sudden, we went from having 2 choices of cars to having 6 choices of cars, right? And it becomes like 2 for the transmissions and then 3 choices each for the engines, and we multiply those together. And this is basically the fundamental counting principle. In this context here, what we would say is, as far as colors, we've got 9 different choices. So if everything else was the same, we have 9 different cars, if you call different color cars, different cars. We have 3 different types of engines that we could choose. And then we've got 2 different types of transmissions that we could choose, 3 different body styles, 2 different interior designs, and then 4 different stereo choices, stereo systems. And what we end up doing is we multiply all of these numbers together to indicate the different choices that we could possibly have with these cars. And multiplying all these together gives us 1,296. So we would say 1,296 different cars are available. And that illustrates the fundamental counting principle. Now we're going to look at another problem that also illustrates the fundamental counting principle. How many different non-personalized passenger car license plates are available in California? And I want to point out that the license plates for, say, pickup trucks or motorcycles, they have a different pattern than license plates for passenger cars. For a passenger car, you have a number followed by a letter, and then a letter, and then a letter, and then a number, and then a number, and then a number. Those are the 7 digits of a car license plate. So in these 7 positions here, well, we have choices for each position. For the numbers, how many 1-digit numbers do we have? We might think 9, but we've got to count 0 as well. So there are 10 possibilities for the first digit of the license plate number. As far as the letters, of course, there are 26, and so 26's go in the next 3 blanks. And as before, what we're going to do is we're going to end up multiplying all of these numbers together, but we're not done yet, because there are the last 3 1-digit numbers, each of which could be one of 10 digits. And so the number of license plates available, 10 times 26 times 26 times 26 times 10 times 10 times 10, and I get a total of 175,760,000 license plates available. Of course, by this point, a bunch of them have been used up, but these kinds of problems don't take that into account. We're now going to turn our attention to permutations. Permutations are kind of a special application of the fundamental counting principle. And here we have a problem. How many ways can a committee consisting of a president, vice president, and treasurer be selected from a group of 10 people? We're going to use the fundamental counting principle, but then we're going to see how this it gets embedded into a slightly different context, that being permutations. First of all, we have 3 positions open, right? We've got the president, the vice president, and the treasurer, that we're trying to fill. Let's say like we're going to select the president first. Well, how many choices do we have for president? Well, there are 10 people. So for president, we've got 10 possibilities. But then once the president is selected, how many people are left for vice president? We only have 9 that are available to be vice president. And once the vice president is selected, then there are only 8 people that would be available for the treasurer. And so the answer here is 720. Now this is, as I said, it's basically the fundamental counting principle, but in this particular context, what we're doing is we're picking 3 people from a group of 10 to be particular officers, let's say. And in this case, what we would say is that order matters. That is, if the person that was selected for president was actually the vice president instead, and vice versa, then that would be a different representative committee, you see. So it matters who's doing what. And when order matters, we're looking at permutations. And the way we denote this is P with a parenthesis 10, 3. So out of the group of 10 people that we talked about to begin with, we're picking 3 of them. 1 to be president, 1 to be vice president, 1 to be treasurer. And this is actually a button in your calculator. It might look like little n, p, little r. And in this case, the n is 10 and the r is 3. Okay, so generally what we would say, we would have p, n, comma, r. Now that's just the notation, but that doesn't tell us how to figure it out. The formula for p of n, comma, r, or permutations of n things taken r at a time, that's how math people say that, is n factorial divided by n minus r, in parentheses, factorial. So let's see how this works out with the numbers that we were looking at just now. So the permutation of 10 things taken 3 at a time is going to be 10 factorial divided by the quantity of 10 minus 3 factorial. Well, this simplifies to 10 factorial divided by 7 factorial. And as you may recall, 10 factorial is 10 times 9 times 8 times 7 times all those numbers down to 1, which means it's 10 times 9 times 8 times 7 factorial. In the denominator, we have 7 factorial. And when those divide out, we're left with simply the 10 times 9 times 8 that we had originally come up with. That's 720. Now, this being a word problem, we should answer it using a sentence. So, and you might say this is a cop-out, but 720 such committees are possible. I didn't want to write down the president, vice president, treasurer. You don't have to either. But these are permutations, and this is what happens when we care who's doing what, right? In other words, when order matters, then we're using permutations. And as I said, this is likely a button in your calculator, and if you don't see it right away, it might be in a probability menu. It might be in the PRB menu.